Hello everybody, thank you for joining our talk. As he said, our paper is called Towards Predicting Efficient and Anonymous Tor Circuits. This is a joint work done by myself and my co-author Mohsen Imani at UTA. Also, my co-advisors Jiang Ming at UTA and Matthew Wright at RIT. So the key concepts that you should understand about the Tor network to understand this talk is that Tor is an anonymous communication system where users can access the internet anonymously by first building a 3-hop circuit through the Tor network. The first hop is called a guard, the second hop is called a middle, and the last hop is called an exit. In the Tor network, there are over 7,000 volunteer relays distributed throughout the world, and there are millions of users. So this architecture makes it very difficult for an adversary to link the client to her destination. For example, if we have a passive adversary that can observe the traffic from the exit to the destination, they won't have enough information to link the client to her destination. And likewise, if an adversary can view the traffic from the clients to her first hop, the adversary wouldn't have enough information to link the client to her destination. Tor is slower than typical web browsing, and it is this architecture that gives rise to some situations where clients may have a poor or slow connection. For example, say you have a client who builds a circuit, and the client is in North America, their first hop is in Europe, their middle hop is all the way back in North America, and their last hop is in Australia. And say they use this circuit to connect to a server in California, this would be one situation due to Tor's architecture that this client would experience a slow connection. Congestion in Tor is also an attribute that may cause clients to experience slow connections. For example, congestion is caused by a large subset of users consistently selecting the same node in most of their connections, causing that node to be overloaded with respect to its computational resources, but also with respect to its bandwidth resources. A way to mitigate congestion and latency in Tor is by strategically selecting paths through the Tor network. Now I'm going to discuss 3 path selection algorithms. The first one is bandwidth-weighted selection, which is what is currently being used in Tor. Then there's Snader and Borisov selection and congestion-aware routing. In bandwidth-weighted selection, the client randomly selects 3 nodes through the network, except the selection is not done at uniform random. It's done weighted towards bandwidth so that nodes with higher bandwidth have a higher probability of getting selected compared to nodes with lower bandwidth. But in this type of selection, there is a trade-off where if we weight too heavily towards bandwidth, then we cause too many users to select nodes with higher bandwidth, thus causing bottlenecks in the network. Snader and Borisov path selection is an extension of bandwidth-weighted selection, except the user is given a tunable parameter in the range from 0 to 15, and the parameter controls how much the selection is weighted towards bandwidth. So if the tunable parameter is set to 0, then 3 relays are chosen randomly, and bandwidth is not considered. But if the moderate parameter of 9 is chosen, then the selection will be moderately weighted towards bandwidth. And if the parameter of 15 is chosen, then the selection will be heavily weighted towards bandwidth. And again, there's a trade-off where when we weight the selection too heavily towards bandwidth, we cause a bottleneck in the network because we're causing a lot of users to use only nodes with high bandwidth. In their study, they showed that when the tunable parameter is set to 9, they get the best results with respect to the bandwidth congestion trade-off. Congestion-aware routing is another routing protocol where the client makes round-trip time measurements from their location all the way to the exit. And from the round-trip time measurements, they're able to infer congestion. And the round-trip time measurements are made during circuit creation, but also over time through application measurement. And they preemptively build a pool of circuits, and for the rest of their connections, they use a circuit with the lowest round-trip time or the lowest congestion. But one disadvantage for this method is that if the exit node is malicious, then they can game the round-trip time measurements, and they can win more traffic, they can put themselves on more connections, and they can increase the probability of de-anonymizing the user. So to mitigate congestion and latency in Tor securely, without adding more bottlenecks, we propose PredicTor. PredicTor is a machine learning approach where first we probe the network and build a training set, then we model the training set with a machine learning model, and then we port that model to clients. And then from there, clients can make future predictions about their circuits. So in particular, we deploy a trusted authority, and this authority builds circuits through the Tor network and makes connections to internet destinations. And over time, they build a training set where each data point consists of a guard, a middle, and an exit, and the training label consists of the download time. We model this training set with a machine learning model. In our experiments, we did KNN and random forests. And then we port this model to all clients via the consensus documents. Each data point in the training set consists of, like I said, the guard, middle, and exit. And from these relays, we extract features. We extract the autonomous system as a feature. And autonomous systems make up the transport layer of the internet. So AS as a feature would imply network connectivity and also network location. We also extract bandwidth from the consensus documents, and we extract the country code, which is another feature that implies location. For the training label, we take the median of the download times from the training set, and if the download time for this particular example was greater than the median, we would label it as false, meaning slow, and if it was less than the median, we would label it as true. So we come out with a binary classification task. So to evaluate the accuracy of this method, we did two experiments, one on Shadow as a simulation and one on Live Tor. Shadow is a discrete time event simulator that allows us to simulate a scaled down version of the Tor network on one machine. So we simulated 1,000 clients, 400 relays, and 70 servers. And we built a training set by first building paths through the Tor network using Tor's bandwidth-weighted protocol and downloading files of 320 kilobytes. And so for one simulation, we built a training set of 120,000 streams. Then we ran another simulation with a new seed and built a testing set of 25,000 streams. On the Live Tor network, we deployed a server and hosted 20 instances of Tor, and we built paths through the Tor network, and we connected to a US destination server and downloaded a file of 80 kilobytes. And over the course of 1 hour, we built a training set of 50,000 streams. And then over the course of the very subsequent hour, we built a testing set of 20,000 streams. So by fitting this data, training data, with KNN, we were able to predict whether or not the circuit was fast or slow with 70% accuracy on the Shadow simulation and 64% accuracy on Live Tor. But when we fit the data with the random forests, we were able to predict whether or not it was fast or slow with 76% accuracy on Shadow and 70% accuracy on Live Tor. So based on these results, we used random forests in our PredicTor implementation. So to evaluate PredicTor, we implemented it in the Tor source code, and we tested on Shadow and on Live Tor, and we compared it with Tor's bandwidth-weighted selection, which we call Vanilla. We compared it with congestion-aware routing, CAR, and Snader and Borisov path selection with the tunable parameters set to 9, and also with the tunable parameters set to 15. The figure on the right shows a CDF of download times from our Shadow experiment for all the tested path selection algorithms. We observed that PredicTor improved performance by 23% compared to Vanilla in the median case, and by 13% compared to CAR in the median case. This resulted in a speed up of over 500 milliseconds in the median case for download times, and by over 1.5 seconds in the 90th percentile. We also note that SB9 and SB15 had the slowest performance, even though their relay selection was tuned heavily towards bandwidth. The figure on the right here shows our Live Tor results, and it's a CDF of download times for the tested algorithms. And we observed that PredicTor had an improved performance by 11% compared to Vanilla in the median case, and by 6% compared to congestion-aware routing. And this resulted in a speed up of over 1 second in the 90th percentile. We also noticed that SB9 and SB15 had the worst or the slowest performance, even though they were heavily weighted towards selecting nodes with high bandwidth. So this figure shows a CDF of consensus bandwidth for circuits that were created on the Live Tor experiment for all of our test algorithms. And we observed that SB9 created circuits with 22% more bandwidth compared to vanilla, and SB15 created circuits with 97% more bandwidth compared to vanilla. So this indicates that relays with high bandwidth experience long-term persistent congestion due to Tor's bandwidth-weighted selection policy, and that even if one client heavily weights their selection towards these nodes, they will experience poor performance compared to vanilla. This also indicates that performance gains in PredicTor are not solely attributed to bandwidth, even though bandwidth is one of the key features that we select. Some other key findings. This figure on the right is a CDF of the percent of circuits that each relay was selected for the path selection algorithms, and it indicates relay utilization. And this was done on our shadow simulation. We found that SB9 and SB15 utilized 50% of the Tor network, and they ignored the other 50% of relays with lower bandwidth. We also observed that vanilla utilized 65% of the network and ignored the other 35%. And PredicTor had the best load distribution, and it utilized 85% of the network, even though some of those relays probably had lower bandwidth. Some other key findings from our live Tor experiment. We measured the circuit distance taken as a measurement using GPS coordinates from the guard to the middle, and also from the middle node to the exit node. GPS length of a circuit is not a measurement of latency, but it can be an indication of latency. So we measured circuit length for vanilla and for PredicTor in our live Tor experiment, and we found that PredicTor built circuits that were 680 kilometers shorter compared to vanilla in the median case. So we conclude that PredicTor performance gains are due to avoiding nodes with persistent congestion, also due to better relay utilization and load distribution, and also because PredicTor builds circuits of shorter geographic distance. So to evaluate the security of PredicTor, we looked at the literature, and we looked at anonymous metrics in the literature for anonymity. And we found that entropy-based metrics do a good job of measuring anonymity in the average case, but they tend to fail for the special case, or for the worst case. We also looked at all or nothing compromise, and it is a good measurement of anonymity once clients become compromised, but it leaves a blind spot in which we don't know the state of anonymity until the client has been compromised. The ANOVA framework was closest to what we needed, and we modified it so that it would consider any number of clients connecting to any number of destinations using any user model. We also modified it so that it would measure the client location leakage based on the relays that the clients select. So this anonymity metric we propose is called CLASI. It stands for Client AS Inference. And CLASI is a challenge response game similar to the ANOVA framework. The adversary is given a path simulator that consists of any number of clients connecting to any number of destinations. And the adversary gives the path simulator to the challenger, and the challenger uses it to generate one path, P prime in this diagram. And they remove the client from this path, and then they send the path back over to the adversary, and the adversary uses its path simulator along with a classification method to predict the location of the user. Then the adversary sends the location back to the challenger, and the challenger compares. So for the classification model used by the adversary, each data point consists of a guard, a middle, and an exit, and we extract features from those relays. We extract the AS, the bandwidth, and the country code, and it also contains the destination, and we extract the AS and country code from that as well. And the training label is set to be the client AS. So after running several simulations, we get a probability of the adversary's ability to be able to guess the client's AS correctly. And if the adversary can do no better than randomly guessing, then the epsilon in this equation should be near zero. But if the adversary has some advantage in guessing the client's location, then the epsilon in this equation will grow. And so we use epsilon in this equation as a metric to measure what we call sender AS leakage. So to evaluate the security of PredicTor, we measured sender AS leakage for vanilla, car, and PredicTor, and we found that sender AS leakage for CAR was higher than PredicTor and Vanilla, and this is interesting because CAR clients make round-trip time measurements from their specific location in order to select circuits. So CLASI was able to indicate that these clients may be losing some information about their location by selecting circuits that way. And that's an indication that you wouldn't get using an entropy-based metric or a time-to-first compromised metric. We also observed that Vanilla and PredicTor had similar sender AS leakage, and this also makes sense because in PredicTor, we port the same model to all clients, and therefore all clients build circuits exactly the same, similar to Vanilla. To further evaluate the security of PredicTor, we did it on an entropy-based metric called uniformity degree, and we found that PredicTor had slightly less uniformity degree than Vanilla. PredicTor came in at 0.79, and Vanilla was measured at 0.84. In conclusion, PredicTor performance gains, as we observed, are attributed to avoiding congestion because it has better load distribution and also because it builds shorter circuits. PredicTor security evaluation, we saw that PredicTor had similar sender AS leakage compared to Vanilla and slightly better compared to CAR. And we conclude by saying PredicTor had the best security performance trade-off compared to both Vanilla and congestion-aware routing in our experiments. Thank you, and I'm pleased to answer any questions you may have.
Hi, quick question. Do your TCP connections get out of slow start? Did you?
I can't hear you.
Do your TCP connections ever get out of slow start? The file that you're using is only 320 kilobytes, and I noticed the download times are really short. They're like 4 seconds. Most speed tests run for at least 15 seconds.
Okay, so the download times I put here wasn't the real data.
Okay.
I just entered in time so that the listener could get an idea for what we're measuring.
Yeah. So my question though is, did your download test run long enough for the TCP connections to get out of slow start? Because the differences are so small that it looks to me that you might actually just be measuring the effects of slow start on a high latency path. So I was just wondering, do you get out of slow start?
I think I'll have to talk to you later about that because I'm not sure how to answer that. So.
Okay.
Hello. I'm just wondering, it looked to me like you were testing PredicTor in an environment in which everybody else is using some other circuit selection mechanism. Do you have any idea of what it will look like if most people or most clients are using PredicTor? Will you, when it's in a sense is competing with itself or other instances of the algorithm for selecting circuits?
Yes, that's a good question. Thank you. In our shadow simulation, we were able to simulate how the system responds when all clients use PredicTor in the shadow simulation. But in the live Tor simulation, we can only deploy one client. So those results were with one client using PredicTor and all the other clients using Tor's vanilla bandwidth weighted selection.
So maybe this came up somewhere in the security evaluation, but I wonder how a small collection of colluding nodes could try and modify the probability that a circuit is chosen entirely through them, and whether you thought about that and how PredicTor might impact that.
Can you repeat that? I couldn't hear you. I'm sorry.
If there's a small collection of colluding nodes, and they try to induce a circuit to be formed entirely through them, so that they can decrypt the traffic, it's not clear to me how PredicTor would change those probabilities, like change how easy it is for a small group of nodes to break the system in this fashion.
Mm-hmm. Well, all I can say is that we deploy a trusted authority, and so we assume that that authority is trusted and that an adversary doesn't have the ability to modify the input there.
To follow up on the previous one, I do think that though, if you're in a circuit with all of your friends, which you would, you can, like, whether or not you're being measured or not, you can be faster or slower. You can at least slow down in the other cases. But the question I had was about staleness of the data, and how, so you in your cases you did your measurements and then you did your test set immediately after. Do you have any idea on how often you'd have to remeasure and retrain, and how that would compare to the existing kind of bandwidth measurement sort of load that's on the network? Yes, that's a good question. This was basically our first attempt. We measured for 1 hour and then tested for 1 hour on the live Tor network. So we don't know how the system will respond if we varied those parameters. But that would be a good area to continue the study.
Great talk. Very clear and easy to understand. I think that's evident by everyone asking all the questions. First, I'd like to commend you on using Shadow. I think it's important that people use standardized tools. It helps other institutions and researchers compare the results to yours and to reproduce your results, so good job with that.
Thank you.
The question I have is, your experiments, you were downloading the same size file across your experiments, 320 kilobytes in Shadow and 80 kilobytes on the live Tor network.
That's correct.
I'm wondering if you can comment on, if you change the size of the file that you're downloading, how that would affect your machine learning algorithms.
If we change the size of the file, we would have to, instead of taking the time to last byte, we'd have to take the time to first byte. And then the file size shouldn't matter.
So you think you would get the same predictive power by using the time to first byte as time to... The reason I ask is because I run Tor relays, and I've noticed that we see highly dynamic data on our relays, depending on if we happen to be part of a circuit from a BitTorrent client at that point in time. So I think, especially in the Shadow case, having everyone download 320 kilobytes, you're going to get a very similar set of background traffic, which is going to be reproduced almost every time you run the experiment. So that might change a little bit, but we can talk more after.
Okay.
So I just had a question. I wanted to say great talk. And if I'm not mistaken, your Tor clients were in the United States, and wasn't the authority that was doing the machine learning also based out of the United States for its measurements?
In that particular case, for the results I showed here, the authority was deployed in the United States, but then there's other results, additional results in the paper, where we deployed the authority. We did some experiments with the authority in the United States, and then we also did some in Germany and also in Japan. So if we look further in the paper, I think you'll see a little bit more diversity in the results. I hope I answered your questions clearly. If not, please come talk to me later. Thank you.